Composite Navy Propulsor Shaft Design, Development, and Validation Program is a Phase 2 SBIR out of NAVSEA. Phase 1 demonstrated the feasibility of using a fiber-reinforced thermoplastic consisting of an intermediate modulus graphite fiber in a peak resin matrix to construct a submarine propulsor shaft, and identified remaining data gaps to be addressed. Service engineering is a nationally recognized leader in system protection, enhancement, and enabling technologies. Our core capabilities support the warfighter through survivability assessment, identification of areas for enhancement, and through select modeling practices, development of detailed designs that enhance platform survivability. Services focus extends across air, sea, and ground platforms, involving both manned and unmanned vehicles. Recent activities with unmanned vehicles offer new game-changing capabilities to the warfighter as they pertain to transportation and logistics. Service engineering brings numerous multidisciplinary resources to the Phase 2 program to include our subject matter expert in composites and survivability. With over 40 years' experience in the design and fabrication of fiber-reinforced thermoplastic composites, Mr. Luzetsky has pioneered design and manufacturing techniques which have been vetted through various programs. This program seeks to extend the capabilities of submarine propulsor shafts for next-generation platforms by introducing technology that will facilitate an increased usage of non-traditional materials to enable a broadened design trade space and arrangement options for existing propulsor components. The end goal is to improve performance, improve fatigue life, and decrease lifecycle and maintenance costs associated with submarine propulsor shafts by developing repeatable, reliable, efficient, and robust manufacturing processes using low-cost, non-traditional materials, like fiber-reinforced thermoplastic composites. When successful, the data will be used to target existing and future submarine platforms, like Virginia-class and planned SSNX submarine platforms, as well as other naval platforms, and even non-defense and/or commercial applications, including wind energy, rocket motor casings, oil and gas piping, and submersibles for deep-sea scientific exploration. The main program challenge, as NAVSEA defined it, is to demonstrate the feasibility of constructing a high-quality fiber-reinforced composite shaft suitable for submarine propulsor drive systems. The demonstrator and associated data package that result from this effort focus on validation of laminate quality, manufacturing repeatability, and resolution of any existing data gaps that may adversely impact its application to a submarine propulsor shaft. By reducing weight, the technology under development in this program satisfies a need of both military and commercial organizations that require operational performance enhancements over those obtained through the use of metallic shafting. For example, a reduction in weight can translate to increased payload, improved vehicle performance, reduced fuel consumption leading to lower operational costs, and greater range for vehicular payloads. The technology under development in this program involves the application of a graphite-reinforced peak thermoplastic composite to the fabrication of a submarine propulsor shaft. It uses an additive in situ advanced tape placement fabrication process and leverages analytical design tools developed by Service Engineering and vetted with thin-walled drive shafts for rotary wing applications. By demonstrating manufacturing feasibility at a significant weight reduction while maintaining operational performance properties equivalent to existing metallic shafts, the key innovation developed under this effort is the combined application of an existing material and fabrication process to a large diameter, thick-walled submarine propulsor shaft. Currently, Phase 1 of SBIR N231-047 has been completed, and when this chart was developed, we were approximately 60% through the Phase 2 base period. To date, initial material tests verifying the feasibility of a graphite fiber, reinforced peak thermoplastic composite to meet the design requirements of a submarine propulsor shaft have been performed. In addition, further material data has been and is currently being developed to resolve data gaps that exist between a thin-walled small diameter and thick-walled large diameter shaft designed for a maritime application. These tests include fatigue, bearing, and galvanic corrosion. Based on existing available material data, a preliminary design has been developed for a propulsor shaft with supporting finite element analysis, which will be updated as new material data is available. Lastly, a tool has been designed and fabricated to support the manufacturing of a shaft section to evaluate laminate quality, consistency, and repeatability. The activities of the program are designed to support a decision-making process associated with a program of record targeting the development of a composite propulsor shaft for application to the SSNX submarine slated for the early 2040s. This table summarizes the key features, advantages, and benefits of the technology in addressing the Navy's key challenges. These challenges include a material robustness to support the design with a focus on fatigue properties, material and shaft design with high environmental resistance, particularly to seawater immersion, a manufacturing process which is highly repeatable and capable of producing high-quality composite laminates in large, thick, cylindrical shapes, and a structural performance capable of supporting a propulsor shaft operational environment, especially in fatigue loading. Based on ongoing development of a thermoset composite shaft and an impending first procurement date for early 2040s, additional funding will be required beyond Phase 2 to produce and dynamically test a full-size, in both diameter and wall thickness, shaft specimen. In addition to the test article, a test rig capable of testing the required fatigue and static loads would need to be developed since one does not currently exist. These steps are necessary to close the developmental gap between the thermoplastic and thermoset shaft configurations. Due to the early stage of the SBIR other than the TPOC, we are seeking a transition advocate with the initial transition target being the SSNX submarine platform, with a backup being Virginia-class submarine and other submersible, as well as surface fleet platforms. Additional maritime potential transition targets that align with the submarine targets are amphibious ships, military sea lift command, and hovercraft. Alternative transitions include any shaft configuration up to the thickness and diameter developed in this program. Thinner wall shafts have been vetted on various programs, and with program success, the design and fabrication envelope will be expanded up to the size associated with the propulsor shaft and establish a baseline for additional expansions. This opens transition potential to air, sea, and ground platforms and creates an opportunity for numerous commercial uses. In each of the transition targets, the focus is on cylindrical structures. In addition, based on other research conducted by Service Engineering, a technique has been developed and demonstrated to integrate electromagnetic shielding directly into the thermoplastic laminate without impacting material properties. Various Navy organizations have recognized needs for the technology developed in this program. To aid in the decision-making process and transition to NAVSEA platforms, a facility and equipment capable of mechanically testing a propulsor-sized shaft is required. In addition, multiple shaft sections of suitable size to test and evaluate for laminate quality and structural integrity would be necessary. Beyond recognized DoD transition opportunities, there are other areas that could benefit from the technology, but require certain considerations and needs to facilitate the transition, such as points of contact, development of a generic data package, and formalization of the design process. The TRL of the technology can be rated as 5.5 when considering the projected results, but with additional resources, a TRL of 8 or better is achievable. As a recognized leader in system protection, enhancement, and enabling technologies, Service Engineering encourages interested parties to reach out to us to discuss their needs. With a company-wide matrix organization and extensive experience in survivability assessment, design, and analysis, Service Engineering is well poised to address the needs of customers interested in the technology developed in this program. Identified are points of contact that can assist in assessment of the technology for a specified application and/or provide the resources to transition the technology to development, prototyping, or production.